Hello everyone, and welcome back to another Eng 130 midterm tutorial. So in this tutorial, we're going to be covering the 2011 midterm and chapter question 3. And in this question, what it would like us to do is it says that the motor in figure 3 is suspended by a massless platform and 3 massless ropes. Blah, 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 blah. So basically what it says, we have 3 ropes, AB, AC, and AD, and that's probably the most important part. And they're all joined at a ring at A. And if you guys know where this is going, it's obviously going to go to particle equilibrium, so let's just keep going real quick. The maximum force, and that should be your first worry, is when it says maximum force, because that means that the forces in those wires, they could be anything. However, they all have to be below or equal to the maximum. And it says that the maximum capacity of each rope is 100 kilonewtons. So what this means is all those forces in those ropes, they could be, like I said, they could be anything, as long as none of them are over 100 kilonewtons. And then finally, it says that a chain AE, so that's this little part up here, it's kind of hard to see, has a maximum capacity of 5,000 kilonewtons and suspends the overall assembly from the roof of the structure. So yeah, you guys can probably just guess this by intuition, but this last sentence here actually is kind of important, because what that means is that force AE, it supports everything below it. So whatever the mass of that motor is, that's going to be the mass, or I guess the force in that is going to be the motor's mass times gravity. And then of course it also says using appropriate free body diagrams in your solution, and then it wants us to do the following 2 things. And normally with these questions I would read out one of them and then I would do the second one, but these ones are actually kind of interlinked. So this question is actually just one giant problem. It just doesn't explicitly say that. So the first one says find the maximum mass of the motor in kilograms by solving which rope will break first. So it's again one of those things that we don't know any of the the forces in the ropes. But once we do a free body diagram, we can use our special trick of elasticity to find all the forces in the rope. And the reason why I said these are kind of the same 2 questions is if you look at the second one, it asks for what is the force in the rope just before the first one breaks. So by particle equilibrium, when we solve these systems of equations, what we'll find is we'll solve for everything at once. So even though it's a separate question, by solving for part A, we've already had the solution for part B. So it's just one giant question. And if we go into the question, we can kind of see we have a particle equilibrium at A. So one of the first things that we should always do in these cases is draw a free body diagram. So let's just look at point A for a second. So particle equilibrium, we know all of our forces act at a single point, which we'll have as point A. And in these, we're going to have to start drawing all the forces. So again, this is one of those things that 3D, it's always kind of hard to figure out the right free body diagram. So what I like to do is I just draw all the forces real quick. So here's one force going out. And then we see that we kind of have 3 coming at the bottom. So we'll do this force. We'll do the force out to the side. And then finally, we'll do our last force, which goes way kind of to the left. So as you guys will see, this doesn't look like it's to scale. It looks like a whole lot of nothing right now. It kind of looks like if a child were to draw a spaceship. But what we can do is we can start putting in all the dimensions we need. Because remember, in the end, all we want is this free body diagram is able to solve everything we want to solve for. It should contain all of our information. So we know that this is going to be point A, and the top we know is point E. The bottom we have point D. The very, very bottom we have point C. And then on the side we have B. And what I'm going to do is I'm just going to put the points of all of these. Well, point E, we don't know, but it's okay because we learned that we don't need it, and we'll explain that later. Point A, we do know. We know it's going to be 0, 0, 3, and that's in meters. Looking at point D, first thing that we're going to want to do is look at how far it is along the x-axis. And if we look at the x-axis, which is right here, we see that it goes a distance of -2 meters along the x-axis. So we're just going to put -2. We know that it's right on the y-axis, so this point right here is going to be 0. And, oh, sorry, not 0, 0.5. And then our last point is going to be 0 because it's 0 in the z direction. And we can go through and say, okay, well, if we look at D, we know that it's going to be 1, 1, and 0, and that's in meters. And of course, point B is going to be 2, -1, and 0, and that's in meters as well. So the Hardest part of this is really just figuring out what are all the dimensions I'm looking for. And once that's done, we can start putting in our unknowns. So remember, we said point E, it doesn't really matter, so I'm going to erase the bracket. But our unknowns, let's put in red so they really stick out. So we're going to have this as tension AD, because it goes from A to D. Same with this one, it's going to be AC. And then finally, we've got tension AB. So we have our three unknowns at the bottom, but remember, we also don't know what's at the top too. So this can be tension AE. And then this is where you guys have to try and get the hint of what it means to find a maximum. Because if we look at this really quick, we can easily see, hey, we got 4 variables, but we only have 3 equations. So the system, the way it is right now, we can't solve it. We're going to have to do something special later. But before we do that, one of the best things to do is just, okay, what are our free body, what are our 3 equations? So remember, I said we have 3 equations, and for this motor to be truly stationary, it's going to have 3 forces. Some of the forces in X equals 0, some of the forces in Y equals 0, and some of the forces in Z equals 0. So it's just like 2D. The only problem is we always know that for 2D, if we're finding a component of it, let's say the X component, it's typically F times cosine of theta. And that cosine of theta will give you a number less than 1, less than or equal to 1. Say it's 0.6. So just for example, we can say that Fx is equal to 0.6 times F. And this is great because then we can throw that in our sum of the forces in X. But the only problem that we have for 3D equilibrium is if we look at this 0.6, it's that coefficient in front of the force. And well, how do we get those in 3D? And the answer is actually going to be unit vectors. Because what a unit vector does, and I'm just going to switch to black for a second. So if we had a unit vector of a force, and let's just say for fun, I'm just going to write random numbers down, but it's 0.6i minus 0.7j plus 0.1k. And again, this is probably not a unit vector. The magnitude is probably not equal to 1. I'm just putting random numbers down. But this is how you get those components in front of your f. So this right here, this would be the component for fy, or sorry, fz. This component would be for fy. And finally, this would be the component for fx. So if we find the unit vector of all these forces, we can very, very simply get all those coefficients and we can easily create our equations. So I'm just going to erase this real quick, get it out of the way because it's just going to confuse you otherwise. Bye-bye. See you later. All right. So let's start finding the unit vectors of everything and just see how it goes. So first one that we're going to have is FAB. Let's start with A and go to C and then go to D. So FAB. So let's put this here. And yeah, we're trying to find the vector. So why not throw a hat on top? So we know that a unit vector for AB is going to be equal to the position vector AB divided by the magnitude. Oops, I was going to write down the magnitude equation, but we're going to get there in due time, don't worry. So this will be divided by the magnitude, RAB. Let me put the line down. Perfect. So if we can find those two things, we're good to go. Well, we can't find the magnitude RAB without finding RAB first. So the first thing that we're going to do, let's find RAB. So let's go RAB. And we know that this is going to be equal to the coordinates of B minus the coordinates of A. So remember, it's where we end up minus where we started. So if we're going from A to B, we end up at B. So we're going to take the coordinates of B minus the coordinates of A. So what would this mean? Well, if we put in brackets, what are the coordinates of B? We know that they're 2, -1, and 0. And we're going to subtract the coordinates of A, which are 0, 0, and 3. So 0, 0, and 3. So it should be pretty simple. 2 minus 0, well, we know that that's going to be 2. And this will be in the I direction. -1 minus 0, well, that's just going to be -1 in the J direction. And finally, 0 minus 3 is going to be -3. And that'll be in the K direction. And we all know that this will have units of meters because it's a position vector. So if we look at the diagram, what does that mean? Well, to get from point A to point B, we had to go 2 in the X direction. Okay, well, that makes sense. We want 2. We had to go -1 in the Y direction. Well, we did that too. And we had to go -3 in the K direction, which we did. So this is why this is good. It makes sense. So we can also find the magnitude of RAB by square rooting all of those components. We're not square rooting, we square root everything, but what we want to do is square all of the components. So we're going to have 2 squared plus 1 squared plus 3 squared. So we can put this all the way to the other side, and what we get in the end is root 14. So I just like to leave it as root 14. You can put a big decimal number, that's fine too. It's the same number, it works out fine. So for my unit vector, what I'm going to do is I go unit vector AB, and now it's up to you. So this is completely up to you. You guys can put it in decimal form, you guys can leave it as something over root 14, it doesn't matter. I personally like to go just 3 decimal places, so I'm going to start the unit vector, and what I get here is 0.535. That's in the I direction, minus 0.267, and that right there is in the J direction. And finally we go minus 0.802. Oops, I was going to put 820. 802, and that's in the K direction. So I can close this bracket. Vectors of a unit units of a unit vector, well, they're nothing, because if we have something that's meters and we divide it by meters, it's going to cancel out. We got nothing left. And now just real quick, make sure you guys know where I got these numbers from, because remember, you don't have to show all your steps in the midterm, you just got to show your general process. So where does that 0.535 comes from? Well, that's going to be the I components of the force vector, so it's going to be equal to 2 divided by the magnitude of that vector, so 14. And just like that. So 2 over root 14, we get that 0.535. All right, so far it's looking pretty good. Now what we can do is we can move on to the same thing for FAC. So I'm just going to write FAC. And now this is one of the questions I always get. So the first time I showed all the steps, I wanted you guys to really see where I'm getting all those values from. But now I'm going to get to the most common question is, well, how much work do I really have to show in the midterm? Well, you know what? That's a great question, because of course it's the midterm. You guys are going to want to go fast. You guys aren't going to want to dick around and show a bunch of work when you don't have to show any work. So if this was me, what I would do is this. I would go R, and this is going to be kind of the bare minimum you need, in my opinion, to get marks. So we know that RAC, well, actually what I would do is this. I would go RAC is equal to RC minus RA. So show, you know that what it is. And then what I would do is I wouldn't show the subtraction. I would just go right to the vector. So in your calculator, you guys can easily figure this out, because it's going to be, I put RC minus RC. RC minus RA is late. I'm sorry, you guys. So if we look up here, and similar to the first one where the X and Y component will just come from RC, and then the K component will come from RA. So if we look up at the X and Y of C, it's 1 and 1. So what we're going to have is 1I plus 1J, and it's going to be minus the component from RA, so minus 3K. And that is going to have units in meters. So the next thing I would do, I'd find the magnitude of it all, but instead of just throwing it all in there, because I know that everything is a function of that position vector, I would just go UAC is going to be equal to, I'm just going to put RAC divided by the magnitude of RAC. And what I would do is this. I would put RAC at the top, so we know it's going to be 1I plus 1J minus 3K. And that. And then right at the bottom, I put the calculation. Oops, that line was supposed to go straight on me, but it didn't. And then right at the bottom, come on. Oh, there we go. I put in the calculation for the magnitude. So I wouldn't do the magnitude in a separate calculation if I was on the midterm. I would just do it something like this. So it's straightforward. You're still kind of showing all your work, all your steps. So it's not like they're going to say, well, I couldn't follow what you did. It's still very clear what you did. And what I can put is UAC is equal to, and then I just throw in all my decimals. So for this, I get 0.302I, and then I get plus 0.302J, which makes sense because both the x and the j, the I and the j component are both 1. So this one will be j. And finally for the k, I get minus 0.905. So in the bracket, we're good to go. So there's another unit vector. Didn't have to show as much work as the first one, which kind of what you guys want to go for. I know you guys. Let's be honest. There's not one of you guys saying, oh, Clayton, I want to show as much work as possible because it's so much fun. No, of course not. I know a lot of you guys would just want to give me the unit vector and show nothing else. But unfortunately, that won't, that won't work. You can try it, but it won't work. So finally, we got FAD. Same process as before. Let's just write that RAD is going to be equal to RD minus RA. And we know that this is going to be equal to, and I can put in the vector, so it's just going to be the I and j from D minus the k from A. And if we do that, what we're going to get is negative 2 plus 0.5j. And then again, minus 3k. And that would be, of course, in meters. So what we can do now is we can go straight to the unit vector. So we know that the unit vector AD is going to be equal to the position vector AD divided by the magnitude of the position vector AD. So something like this. And we know that once we throw all, oh, actually I should put in the math. Even I'm getting too lazy for this. We don't like showing our work either, but we have to. Trying to mark some of the finals when a professor gives you the key and the key has just very, very little information on it, oh, it's a nightmare. So we should almost get doctor marks. So I just put the position vector at the top. Then at the bottom, I'm just going to go across, and I'm going to do the calculations for the magnitude, which we know are going to be 2 squared plus 0.5 squared plus 3 squared. I can throw this all the way across. All right, now we know that this is going to be equal to, and I'm just going to move it back a bit because I usually run out of room on these unit vectors. We know this is going to be equal to, then brackets. First one I get is negative 0.549. 549, and that's in the I. For the j component, I get plus 0.137, and that's in the j. And then I end up with minus 0.824 in the k. And we can end this, and of course unit vector has no units, so we're good to go. Now if we look at the free body diagram, we found the unit vectors for all those TAB, TAC, and TAD. So we're looking pretty good right now. Looking pretty good. Now what we can do is we can start taking the components of those unit vectors and deriving our 3 equations. So remember, 3D, so I'm just going to write this down so everybody knows. So we got 3D scenario. Therefore, we have 3 equations. So the first one can be sum of the forces in the x direction is equal to 0. So, all right, so how do I get that equation? Well, what I want to do is I want to take the x component of all of those unit vectors and multiply them by the respective force. So if I go FAC, or no, I guess FAB is first. FAB for the I, we get 0.535. So what this would mean is my 0.535, then I want to multiply by that force. So this would be FAB. I look up at FAC now. I look at the I component 0.302. What does that mean? Well, I'm just going to go plus 0.302. This is going to be FAC. I do the last one for FAD, which is minus 0.549. And that's FAD. And we know that since it's in equilibrium, all those forces must equal 0. So there's my first equation. All right, so I can do the same thing moving on. So I could go to the sum of the forces in the y. So instead of looking at the I component, now I'm going to start looking at all the j components. So I look up at UAB. It has negative 0.267 for j. So negative 0.267, and that's in the j direction. I'm sounding so stupid right now. It is in the j direction, that's correct, but we're multiplying it by the force it has to do with. So it's going to be FAB. We look at UAC, it's plus 302. So I'm going to go plus 302, 0.302. This is going to be FAC. And then my final one, which is right there, is going to be plus 0.137. And it's going to be FAD. And again, this is equilibrium. It must all, of course, equal to 0. So my third equation, sum of the forces, and this one's going to be in the z direction. And this one's always less common because, well, not less common, but this is the one you guys are least used to because in 2D, this is the one that we don't have. Remember, in 2D, we only have 2 equations. So this one's going to be nice and easy because we're going to do the same process, except we're going to look at the k component. So for UAB, we have negative 0.802. So we're going to have negative 0.802. This one's going to be times FAB. And I already know that these ones are all negative. So if I look up at UAC, it's negative 0.905. 0.905 FAC. And then minus. And then the last component, which is right there, negative 0.824. So minus 0.824 FAD. Now, a lot of you guys would put equals to 0, but we know, actually, I'm not going to put equals 0, but we know that there's actually a third force here, and some of the forces in the z. And if we look up to the very top, I'm just going to highlight it. It's this one right there, that TAE, or I'm going to put FAE. It doesn't matter if you label them as T, as long as you label them as F, it doesn't really matter. But we know that this one's acting in the positive z direction. So it's 100% in that direction, so it's just going to be plus, and I'll put T. And of course it's equal to 0. So now we have our 3 equations. And now the good news for you guys is, as I was told today, professors got together, they discussed it, and they said, if students can get to this point, the systems of equations, which I know you guys all know how to do. I know all you guys know how to do it. And they said, if you guys can get to this point, you can use your calculators to solve it. Okay? You guys are engineers. In the real world, you guys are going to have a calculator. So you're able to solve this using your calculator and give the final answer. So I'll show you guys how to do that. I'm going to show you guys how to set it up this video. And when you guys do that, you guys will be able to see. Now, here's the one thing. If we look at these equations right now, our calculator can solve 3 by 3. So that means 3 unknowns with 3 equations. Oh, we got a problem here because we have 3 equations, yes, but we actually have 4 unknowns. So this is going to, what do we do? We got 4 unknowns. I don't know what to do. This is when you guys are going to have to start using elasticity. Oh, that's a big word, Clayton. What does that mean? Well, honestly, I don't even really know. I'm just kidding. Elasticity is something structural engineers are like, it's drilled into your head what elasticity is. But what it means for you guys, and this is all you guys will need to know, it means that everything's proportional. And I've talked about it so many times, so you guys think, we know Clayton's proportional, big deal. Well, let me just tell you one more time, just so you guys remember. So what it means is that if I have FAB is equal to 1, so let's just write, actually I'll do it in red here so you guys can kind of see what I'm rambling on about. If I go FAB is equal to 1, and I got FAC is equal to 2, just for fun. Actually, let's do this to 3, just for fun. If I were to increase FAB to 3, so I multiplied it by 3, well, that would mean FAC increases proportionally as well. So I multiplied this one by 3, so times by 3. So all I'm going to have to do is times this one by 3, and I'm going to get 9. So that's what it means to be proportional. So all the forces will be related to each other in some way, in the fact that they're all proportional. So that's what we're going to use to solve this, because if we assume one of the forces is 1, we can find out the rest of the forces. So let's just say that FAB, and put this to the side, FAB is equal to 1. So of course this probably won't be our final load combination. It won't be our final load. We're going to have to multiply it. But what's nice is if we can solve all the other forces, we can find their proportionality to each other, and we can multiply them all together to make things really, really easy. So you know what? I'm going to solve this by algebra because This one's actually not that hard. I think you guys know how to do it really, really fast. So the first thing I like to do when I start solving these algebras, these algebraic equations, I just want to label my equations so I can refer to each one. So I got equations 1, which is sum of the forces in x. I got equation 2, sum of the forces in y. And I got equation 3, which is sum of the forces in the z direction. Okay, well, where do I start? Well, I want to usually start with the one with the least amount of variables. And if I look at 1 and 2, well, they're going to be kind of the exact same because I know FAB is 1, but they both have FAC and FAD. So I'm not going to really get away with anything. So let's just start with equation 1. So right here, I'm just going to go 1. And what I want to do is I'm just going to write down, okay, well, if I look at equation 1, I got 0.535 times FAB, but remember, FAB is 1 now, so we're just going to put 1, so it doesn't matter, and plus 0.302 FAC. We don't know what FAC is, so we still have to include it. And then we know that I can move the FAD, because it's negative, to the other side to make it become positive. So 0.549 FAD. Okay. Well, this is kind of nice because now I can get one of the variables as a function of the other variable. Okay, so let's do FAD, because all I have to do to find FAD is just divide both sides by that 0.549. So if I do that, what I get is FAD is equal to 0.947, or is, 974, and that's just the 0.535 divided by the 0.549. And what I'm going to do is I'm going to add 0.550 times FAC. And where does that 550 come from? Well, that's just 0.302 divided by the 0.549. So this right here, this is going to be my next equation, and this is going to be equation 4. All right, well, we're making good time now. So what do we do? Well, let's take that equation 4 and let's throw it in to equation 2, just for fun. Let's go have some fun. So the first thing that we have in this equation is negative 0.267 times FAB. Well, actually, we know that that's 1. So let's just leave that. And then plus 0.302, and this is times FAC. We don't know FAC yet, so we can't do anything about it. But here's where it gets kind of fun. Is then we go plus 0. And if I look up 0.137 times FAD. Well, we actually know FAD. It's 0.974 plus 0.55 times FAC. We know that this is equal to 0. And what's really, really, really nice now is I have one equation and there's only one unknown, and that's FAC. So from here, I can start rearranging things to solve for FAC. So if I move all the constants to one side, I get 0.377. And if I move all the FACs to the other side, I get, if I move all the FACs to one side, I get 0.377 FAC. And if I move all the constants to the other side, I get 0.134. So therefore, I can just divide by the 0.377. I get FAC is equal to 0.354. So that's perfect. I know that the number shouldn't be crazy huge, because remember, this is just proportional to the FAB is equal to 1. So this isn't the final answer yet. That's not the actual tension in the cable. That's a proportion of the tension that's actually in the cable. However, we can use this now to go back and say, okay, well, if we look at FAD, so if we look at equation 4, we can actually just throw in FAC to say that FAD is equal to 1.169. So all I did there, because if I look at equation 4, it's 0.974 plus 0.55 FAC. Well, we know FAC, so we can easily solve it. We have our third equation. So at this point right now, I'm just going to highlight this in purple, or actually let's do pink so you guys can all see. We have FAC, we have FAD, and if we go up to the top Where is it? Right here. We also have FAB because we just assumed it's 1. And that's fine for now. So we actually have 3 out of the 4 already. So, okay, well, Clayton, well, we're not done yet. We got one more to solve for, and you're right. Well, that can easily solve for equation 3 because we're solving for a t. So if we look at equation 3, that's some of the forces. We've got negative 0.802 times FAB, which is 1, minus, and we go up more, 0.905 FAC, 0.905. This times FAC, but we already know that that's 0.354. And then minus, let me go up to the top again, negative 0.824. 0.824 times FAD, which is 1.169. So far there's no unknowns, but remember we had that plus W, or W. Remember, you can name variables whatever you want. And here I put it as T. So plus T equals 0. So all I have to do is move all that negative crap to the other side. And what I get is that T is equal to 2.086. Perfect. So now what I like to do is I solve for everything. All my knowns are solved for in some sort of factor, some sort of number. Remember, these aren't the final forces yet. So if I were to make a quick table, what I'm going to do is write down all the variables. So we got FAB, we got FAC, and we got FAD. And finally we got T. T. All right, well, let's write down what I had for the variables. So we know FAD is 1.169. We know that T is 2.086. We know that FAC is 0.354. And then we know for the top one, it's just 1, because we assumed it to be 1. And we have 2 criterias right now. We know that, and let's put this in pink, purple real quick. We know that the T has to be less than 5,000. And I know I didn't do the less than sign right. I had a lot of trouble. I remember people say, well, the alligator eats something. Well, who cares? I'm not an alligator. And we know that these 3 must be less than 100. So it's fairly easy to say, well, if that's our criteria, and at most, at the very most, T is going to be roughly 2 times greater than those forces in the cables, it's pretty easy to say, okay, well, this will never happen. This will never, ever happen. Because if T was 5,000, that would mean that FAD is like 2,500. And we know it would snap a lot quicker than that. So we know what we're going to want to do is take out of those 3 forces, we're going to have to convert one of them to 100. And the easiest way to check is which one's the largest. Well, if we look at this right here, we got 1, 0.345, and the 1.169. So it's easy to see that this one right here, the FAD, this is the one that governs. This will be the largest force. So what we know is at the very end, we want this one to equal 100. Because remember, if we look way up at the top of the question, it says that that's the maximum capacity, 100 kilonewtons. We already said that the 5,000 will never work. The ropes will snap way before that hits 5,000. But in the end, what we want is that force equal to 100. So what we're going to have to do is find a magical factor that when we multiply 1.169 by that factor, it's going to give us that force of 100. Okay, well, how do you find that? Well, it's pretty simple, actually. All we're going to do is take that 100 and we're going to divide it into 1.167. What you'll find is that factor is 85.5. Okay, well, we found that factor. What do we do with it? Well, actually, we're going to multiply everything by that factor. So 85.5, because remember, it's all proportional. 85.5 times 85.5. So if you look here, well, 1 times 85.5, that's going to be 85.5. 0.35354 times 85.5, that's going to be 30.3. And finally, the bottom one times 85.5, that's going to be 178.4. So these are my actual forces. Actual forces. And how do I know they're correct? Well, one of them is exactly 100, which is what we want in the question. The maximum force is 100. We found the scenario where one of those forces is exactly 100. So all those forces in the cables we already found. So even though it says in the question, I believe it's part B, what is the force in each rope, just as it's about to break. Well, we just found that. So we can put that real quick for part B. We know that FAC, or I'll start with FAB, it's going to be equal to 85.5 kilonewtons. FAC is going to be equal to 30.3 kilonewtons, and FAD is going to be equal to 100 kilonewtons. And this is just before FAD breaks. So that's part B right there. So let's put a nice box around it. Beautiful. But then we're going to say, okay, well, we went a little too far. Let's go back and do part A real quick. So part A, it's very simple because we know that the tension in that cable is equal to 178.4. And we know that since it's just acting straight downwards, it's because of it is because of that motor. This is equal to the weight of the motor, which is just M times G. And if we look in this case, we know that M is what we want to solve for. It's the mass of the motor. And gravity, well, it'll tell you. But I think, does it say in the question here? It does not. But what will happen on your test booklet is on the very front page of the text booklet where you write your name, stuff like that, that'll give you the assumptions you use. So it'll say use gravity equals 9.81 or something like that, but it's typically 9.81. Now, this is what's going to get a lot of students. It's this right here. We know that weight is equal to mass times gravity. The only problem is when you take this side right here, we're getting kilograms times meters per second squared. Because remember, kilograms is what we want, and if we're using gravity as 9.81, it's going to be meters per second squared. We know that that unit is going to be newtons. And that's the problem, because we don't have T in newtons, we have it in kilonewtons. So therefore, when I'm doing this equation, and I'm doing mass is equal to weight over gravity, I have to convert my weight into newtons. So this will be 178 for 100. So I'm just timesing by 1,000 divided by that 9.81. If you don't divide by that 9.81, you're going to get well, it's not going to be the wrong answer. It's going to be, let's be honest, it's going to be a wrong answer. We're not going to give you marks for that. But what'll happen is you'll find that your answer is off by a factor of 1,000. And it's very easy to tell because if we put it in, we're going to get 190 kilograms. So right here, I'm just going to put real quick that my mass is equal to 190 kilograms. And it's easy to tell because let's say that I forget about the factor. What my answer would be is 18.2 kilograms. And you guys can kind of just tell by logic. And no motor, no big heavy car motor is going to weigh under 20 kilograms. Like, that's smaller than you guys. So it's just something where you have to kind of think it's realistic stuff like that. Like kilonewtons, that's a lot of load. Therefore, the motor must actually weigh something substantial. All right, but that is it for this question. It's simple 3D equilibrium. The good news for you guys is you guys don't have to use algebra anymore. You guys are able to just solve this in your calculator. So if you want to do it the hard way, well, it wasn't even that hard, let's be honest. But you could have solved it like this. If you want to put in your calculator, my recommendation, assume that t is equal to 1 and get all the other three variables as a function of t. Because t in your calculator is going to be the one that you're going to move to the other side, stuff like that. So it's just my recommendation, but again, you guys know how to do it. You guys will be fine. So yeah, this concludes this midterm example, and that's it for the 2011 midterm. So thank you guys all so much for listening, and I'll see you guys in the next example.